Hi guys, Dr. Tim Kruse. This is elementary statistics, and today we're going to find a confidence interval for a population proportion. All right, think of proportion like a fraction. Now here's the formulas we're going to use, and I'll explain all the symbols here in a minute, but it might be easier if we just start with a nice easy example down here at the bottom. So, for an example, imagine an 80% free throw shooter. I think almost everybody is played a little basketball in their past, so maybe you can relate to this. All right, so they normally make, out of 10 shots, that's what the fraction bar means, out of 10 shots, they usually make 8. But some nights they might be having a bad night and they make 6 out of 10, and other nights they might be having a great night and they're making 10 out of 10. All right, so their actual free throw percentage, all right, P is proportion, a proportion is a fraction. Their actual true overall percentage, usually we don't know that until the end of the season, but we can guess at it just based on some samples where we saw them on some nights shoot 6 out of 10, we saw them on some nights shoot 10 out of 10. Based on our samples, we can guess at what their true free throw shooter percentage would be. So 8 out of 10, what we think it is, it ranges between what we saw one night, 6 out of 10, and what we saw another night, 10 out of 10. So based on those performances, we guess that the true fraction, that the true population proportion will lie between what we think it is. We think it's 8 out of 10, we're just not sure. 8 out of 10, some nights he's a couple shots better, and 8 out of 10, sometimes they're a couple shots worse. So we think it lies between 6 and 10, based on giving ourselves a little bit of insurance here. Gamblers call it a point spread. We think it's 8, give or take 2 points. So it's 8, give or take 2. So think of margin of error as a point spread. All right, let's go back up and look at all of our symbols. All right, back to the original formula here. The true proportion, or the true fraction of whatever we're measuring, lies in between what we think it is. All right, this used to be X bar when we were trying to guess what mu was. We called this X bar. This is our sample. It's the fraction we took from, the games that we watched, the sample. So we think we know what the true proportion is based on what we saw in our sample. This is our best guess. All right, so P hat, that's what that little thing is called. We just say P hat. It's also called a point estimate. It's kind of the same thing as X bar was when we were looking for mu. When we were doing confidence intervals looking for mu, we used X bar, our sample mean. Well, this is kind of the same thing. P hat, a point estimate. It's the fraction of successes in the games that we watched in our sample. All right, it's our best guess at what we think P might be. So notice it's in two positions here. It's what we think it is minus a little bit of error, and what we think it is plus a little bit of error. Now for our specific formula, margin of error is this right here. And these symbols inside here, we need to know what Q hat is. Well, Q hat is what I call the rest of it. It's the fraction of, failures in our sample. So if we think that P hat is 8 out of 10, well then Q hat would be 2 out of 10. It'd be the rest of the shots. It'd be the shots that he missed. Another way to find it is, if I know that this is 8 out of 10, I can take 1 minus 8 out of 10 to get my 2 out of 10. So another way to explain it is, let's say we're watching the weather, and the weatherman, weather girl, weather woman, she says, hey, there's a 70% chance of rain today. Well, that means there's a 30% chance that it won't rain. So this is the chance that it happens. This is the chance that it does not happen. Success and failure. All right, P, this guy right here in the middle, that's the true proportion. P for proportion. It's the true fraction of successes in the population. We're talking about, if we're still talking about the basketball player, it would be over the whole season. At the end of the season, what do we predict his fraction of successes will be? What do we predict that how many he'll make out of however many thousand free throws he took will be? We just watch a couple games. That's P hat. That's our sample. We watch a couple games and we kind of guess what his end of the season proportion or fraction of successes will be. Z of C, this is the z-scores that kind of bracket or fence in our confidence interval. Whatever confidence interval they ask us to do, we need to find the negative z and the positive z that kind of fence that area in. I'll show you here in just a second. N, of course, is the number of samples. In our example, it'd be the number of games we watched. And E is the margin of error. That's the give or take. Think of it as the point spread. It could go 2 points higher. It could go 2 points lower. He could shoot 10 out of 10. He could shoot 6 out of 10. So think of margin of error as the point spread. All right, now one other thing before we get started working a couple of problems is, does my data satisfy conditions for an approximately normal distribution? Remember what we want our distribution to look like. We want it to look like that normal curve, all right? We don't want it, with more people scoring to the left or more people scoring to the right. I want a nice, symmetrical, normal curve. And I'm asking, does my data satisfy conditions to, produce that normal-looking curve? Well, empirical studies found, and empirical is a fancy word for, it just means they watched a bunch of examples, all right? It sounds really scientific, but it's not. It just means based on a bunch of observations. It means we watched a bunch of experiments, and this is what it looks like, what happens. So it's not really based on theory or anything. It's based on what they observed, over a period of time. So empirical studies show that if the number of samples times the probability or proportion of success is more than 5, and the number of samples times the proportion of failure is also greater than 5. Well, if both of those multiplication problems are greater than 5, then you can assume your distribution will be approximately normal. So let's just kind of test this a little bit. How do we check and see if we can expect a normal curve? Let's say we check 5 players, all right? Maybe I'm watching 5 players who I think are 80% free throw shooters. I'm going to check conditions. So I watched 5, let's say games. I watched 5 games. 5 times the proportion of success, that's 8 out of 10. Is it greater than 5? 5 times 0.8 is 4. 4 is not greater than 5. So I'm going to say no, this number of observations is not enough to assume that my curve will be a normal curve. Working out the rest of it here, Q is the rest of it. If the proportion of successes is 8 out of 10, then the proportion of failures is 2 out of 10. And if I have 5 observations, I watched 5 games, times 0.2, that only equals 1, so that's not greater than 5 either. So what it means is I need more than 5 observations to assume that my data will be approximately normal, my data distribution. What if I watch 10 games? Well, 10 games times 80%, that's 8. 8 is greater than 5, so far so good. But what about the failures? It's still, the proportion of failures is still 2 out of 10, and 10 games times 2 out of 10 is 2. 2 is not greater than 5, no. I need more than 10. Let's jump up to 20. I watched 20 games times 80%, that's 16. 16 is bigger than 5, that's good. I watched 20 games, the proportion of failure is 0.2, 2 out of 10. Multiply, that's 4. 4 is not greater than 5. No, that doesn't work. It fails right here. I can't expect my data to be normal. 25 is almost there. 20 is greater than 5, that's good. 5 is greater than 5, that's almost correct, all right? I don't have an equals in there. It's just got to be bigger than 5. So I'm going to say no on this one. I'm going to say 25 is not enough observations because it's not quite bigger than 5. How about one more? So I watched 26 games. 26 times 0.8, yeah, that's good. 26 times 0.2, that's 5.2. That's bigger than 5. Okay, finally, both conditions are satisfied. I would need to observe at least 26 games to assume that my data kind of is distributed normally and looks like a normal distribution curve. And then finally, oh, by the way, technicality, I forgot. Technicality, we don't actually know P, all right? To test these guys, we're supposed to do N times P. We don't actually know what P is. We're trying to guess at it. P hat is pretty close to P. If we do a good job, P hat should be really close to P. So we use P hat instead of P. This is the official formula but we have to admit that we don't know p. So we're going to say, well, n times p hat, our best guess, is pretty close. It's approximately n times the actual true proportion. So we're going to use p hat. It's pretty close. It's close enough. We're going to do n times p hat, our point estimate, and check and make sure that's greater than 5. And then finally, okay, this really is finally, before we get to work on a couple of problems, a pro tip is try not to round while you're doing calculations, while calculating. All right, if you round in the middle of your calculations, you're going to mess up your answer. Your answer is going to be off because you rounded in the middle. So try never to round while you're calculating. If you must round, go at least 4 decimal places. More is better, but go at least 4 places after the decimal. So here's an example with pi. All right, I could round pi really badly and just say it's 3. Well, that's not close at all. I could go 1 place after the decimal and say it's 3.1. That's still not great. Here's what you used in school, 3.14, guys. That's still a bad approximation of pi, but it was good enough for middle school and junior high and all that. All right. Let's go 1 more decimal place, 3.142. We're getting better, but that's still not a great approximation. I wouldn't use this in my calculations and statistics. This is the bare minimum that I would use. 1, 2, 3, 4 numbers after the decimal. That's good. You know, more is better. If you use 5 numbers or 6 numbers or 7 numbers or 8 numbers, the more you use, the better your answer is going to be. And if you can, go ahead and use the exact number. Pi, the exact number is on your calculator. It's on everybody's calculator. So if, for example, you have to use pi in a calculation, don't use any of these rounded numbers because your answer is going to be way off. Use at least 4 decimal places. More is better. Use the actual number if you can. If you can use the actual number in your calculations, your answer will be really, really close. All right, I'm going to work one out here, and then I want you guys to work one. So let's work this one together. In a random sample of 66 professional actors, it was found that 40 of these 66, so out of 66, 40 were extroverts. That means outgoing. All right, they're not shy or anything. Find a 95% confidence interval for what we think the true proportion is. Now remember what true proportion stands for. It stands for all of the actors in the world. I want to know out of all the actors in the world, not just 66, but out of all the actors in the world, I wonder how many of those are extroverts. Well, there's no way we can gather up all of the actors in the world and test them to see if they're extroverts. We don't have that kind of time. I can grab a small sample of 66 actors, and I can test them and find out that 40 out of 66 were extroverts. But this is p hat. This is our best guess at what the true proportion of extrovert actors are. We'll never really know what p is because we don't have time to gather up all the actors. All right, the best we can do is p hat, 40 out of 66. That's our best guess at what p would be. All right, let's organize our information here. N, that's how many you interviewed or tested, 66 actors total. P, that's unknown, that's what we just talked about. We'll never really know what the true proportion is because we're never going to gather up all the actors. We're going to kind of guess at it with our sample. This is p hat, also called a point estimate. So 40 out of our sample of 66 said that they are extroverts. Now you can reduce the fraction. Either one of these fractions is good. This is exact, all right? You didn't round here and you didn't round here. Now, if your teacher or your book tells you to go ahead and use a decimal, well then this is this fraction changed to a decimal and taken out to 4 decimal places. So 0.6061, that's about a 61% chance that an actor is an extrovert. Q hat, well, that's the rest of them, all right? Look at it this way. If 40 of them are, then 26 of them aren't. You're just going to subtract the 40 from the 66. So if 40 are extroverts, that means 26 out of the 66 were not extroverts. They're either extroverts or they're not, all right, for a total of 66. You can reduce the fraction and use this instead if you like. Whenever I use fractions, I prefer to use the reduced fraction. Either one of these fractions is exact. These are good to use if you can. But if your teacher or whatever tells you to round, then it's going to be 0.3939, about 39%. Remember, another way to find Q hat is just do 1 minus P hat. So 1 minus 0.6061 is 0.3939. Remember, they add up to 1 because we're talking about everybody. We're talking about all 100%. If this is about 61% and this is about 39%, that adds up to 100%. If we're speaking decimal, they should add up to 1. Confidence level, that was asked for in the problem. They want a 95% confidence level. Now I got to find the Z number that fences in 95% area in the middle. All right, now I've already told you it's 1.96 there. But let me show you a couple of ways of finding that Z number, that 1.96. Here's a drawing. I'll get to the test conditions here in a second. But here's a sketch of what we're talking about. We want a 95% confidence interval. So I want to try and find out from here to here. That's an interval. I need these numbers from here to here. So if I'm speaking Z, all these numbers are in the Z table, 0, 1, 2, 3, -1, -2, -3, and all the numbers in between. If I'm speaking Z, I want to know what Z numbers fence in. So think of those as fences, and here in the middle, this is fenced in. What Z numbers fence in 95%? Well, if there's 95% in the middle, that leaves 5% left over. Split that in half, we got 2.5% here and 2.5% here. Now, an easy way to figure out what these Z numbers are is to look up this in the Z table. Remember 2.5%, that's 0.025. So if I look on remember I'm over here on the left side, so I'm looking for a negative Z number. I'm looking for what negative Z number produced an area of 0.025. So I grab my negative Z table here, and I'm looking through my areas. These are all my areas, and I'm looking for 0.0250. That's it right there, 2.5%. What Z number produced that area? It's negative 1.9, and then we go up to 6, negative 1.96. All right, another way, if you happen to have this, or if you don't happen to have this, you might just copy it down. On my Z table, they actually have all the confidence intervals figured out for you over here. So we just talked about a 95% confidence interval, which we looked up kind of the hard way, but they already have it written down for you over here. It's both of the 1.96s. It's 1.96 and negative 1.96. In a minute, we're going to look for a 99% confidence interval. That's going to be both of the 2.58s. If you want 99% of the curve fenced in, you got to go from negative 2.58 to positive 2.58. But we're using 95%. We're going to use the 196s. All right, before we go any further, before you want to start, you want to kind of test your conditions and see if you can expect a normal shaped curve. All right, I don't want the peak over here on the left. I don't want the peak over here on the right. I want it exactly in the middle. Can I expect a normal shaped curve? Can I expect my data to be normally distributed? So I'm going to test my conditions, n times p, but we're going to use p hat because it's close enough. Here's n, 66. 40 out of 66 were extroverts. That's success. Multiply this, you get 40 greater than 5. So far, so good. Check the failure rate. 26 out of the 66 were not. That's Q hat. My bad. Let me put a hat there. Whoop, Q hat. All right. So 66 times the fraction that failed, 26 out of 66. Multiply, you get 26. 26 is greater than 5. Both conditions are satisfied. We can expect our data to be normally distributed. So it should look like a normal curve. All right, that's just something you always want to check before you get started. Can I expect normally distributed data? All right, so back to, let me get my picture here. Back to my picture. I know that the true proportion of actors who are extroverts lies in between the 1.96s. If I'm speaking, Z language, if I'm speaking using Z numbers or Z scores, I know that the true proportion is somewhere between the 196s. But what I need the X numbers. I need the story problem numbers. All right, using the numbers from the story, what does the true proportion lie between? I need a low value or a low boundary and a high value or a high boundary. Some people call this lower boundary, upper boundary. Okay? So we switch to our formula here, which I showed you earlier. It's our best guess minus a little bit of error, and our best guess plus a little bit of error. So it's our best guess plus or minus, some give or take, a point spread more or less, a margin of error. Here's the specific formula. So it's our best guess, p hat, a point estimate. That's our sample proportion, minus the z number that brackets in 95%, times the square root of p hat times q hat, and this is divided by n. And I kind of write it left to right like this so I can get it all on one line instead of putting a fraction under the root. Over here, same thing except plus. So it's p hat, give or take a point spread, a margin of error. Let's pop those numbers in there. So p hat 0.6061 minus the z number. Now don't worry about negative or positive. Just put your minus here and your plus there. It'll work out. So the z number for that confidence level is 1.96. Square root, here's p hat again, times probability of failure or proportion of failure divided by how many? 66. Same thing over here. The only thing you're going to change is plus. And we wind up right here, 0.49 less than or equal to p, less than or equal to 0.72. All right, let me show you this on the graphing calculator. Let me go back up there and press enter just to bring it back up. I just want to show you how I entered it on the 84. You can do the same thing on pretty much any calculator. There's 0.6061 minus 1.96. You don't need a times right there. You just open up the root. And here's p hat again, 0.6061 times q hat, 0.3939, divided by n, which is 66. And I hit enter, and I get my 0.49. That's my lower boundary. Now, you don't have to type it all in again. All right, on the 84, on the graphing calculator, on the 84, you just arrow back up and hit enter, and then just go over and change the minus to a plus like this. I'm just going to change that to a plus, hit enter, and there's my 0.72 over here. All right, you guys on the 83s, you can do the same thing with, it's called entry on your calculators, and it's in yellow. You can do second function entry, and it will pull up the last entry, and you can edit it without typing the whole thing in over again. All right, so our final conclusion here is we are 95% confident, that was our confidence interval, we're 95% confident that the true proportion p, that true fraction that we're kind of guessing at, that the true proportion p of actors who are extroverts is somewhere between 0.49 and 0.72. So if we're talking proportions, these should probably be fractions. That's 49 out of 100. So we think the proportion of actors who are extroverts could be as low as 49 out of 100, or it could be as high as 72 out of 100. All right, I'm just speaking fraction because they're talking proportions. We answered as a decimal, which is great. But if you're talking proportions, you really should answer, or think of it at least, as a fraction. So the true proportion p, we're not sure, we're guessing at it, but we're 95% sure that it's somewhere between 49 out of 100 and 72 out of 100. All right, and this is my last example here, and I want you guys to try this one. So work it the same way. In a random sample of 504 judges, it was found that 295 of them, so 295 out of 504, were introverts. That means kind of shy, withdrawn, they like to be by themselves. Find a 99% confidence interval for P. So work this the same way as the one I just worked with you. Just go ahead and pause the video, work it out, and then, press play on the video and kind of check and see how you did. All right, let's go through this. Hopefully you paused it and worked it out by yourself. How many? We sampled 504 judges. What's the true proportion of judges that are introverts? Nobody knows, all right? We would have to go find every judge in every country in the world and measure them and see how many were introverts, and we're not going to do that. So we don't know what the true proportion is, the true population proportion is. What we do know is our sample proportion, which we call p-hat, or a point estimate. So we know our sample, out of 504 judges, we know 295 of them were introverts. So this is the best number to use as a fraction because that's exact, but if your book or teacher tells you to change it to a decimal, go at least 4 decimal places, 0.5853. That rounds up to about 59%. So about 59% of judges are introverts. Now what about the rest of them? The ones who are not introverts, that's Q-hat. Easiest way to do it is 1 minus whatever P-hat was. So going back to my weatherman example, if there's a 59% chance of rain, that means there's a 41% chance that it won't rain. You just subtract this from 100%. Now we're speaking decimal, so we're just going to subtract it from 1. So 1 minus the chance that they are introverts gives you the chance that they are not introverts. And make sure they add up to 1, or 100%. What confidence level? This time they asked you for 99%. All right, 99%. If you're going to look it up in the Z table, this is 99%. That leaves 1%. So I got a 0.5% here and a 0.5% here. You need to look up a 0.5% in the Z table, and it should fall under negative 2.58. Or you can use the confidence level thing that I showed you earlier. So we're looking at from both of the 2.58s, from negative 2.58 to 2.58. If you draw a fence there and a fence there, that's going to fence in 99% of the area. Let's check conditions real quick and make sure that we expect our data to be normally shaped, to be normally distributed. N times P hat, 295, that's fine. N times Q hat, 209, that's great too. So everything's fine. We expect a normal distribution just like this picture. All right, now I know the true proportion is somewhere between the 2.58s. If I'm speaking z-score, I don't want to speak z-score. I want to use x numbers. I want to use numbers that are in the problem. All right, so I need to know what's the true proportion or true fraction of judges that are introverts. It's somewhere between what and what. So we're basically going to convert these z-scores to x numbers. All right, using our formula here, let's just go ahead and go down to the numbers. P hat, 0.5853, minus the z that fences in your area, 2.58. There's P hat again, there's Q hat, you're multiplying, and then you divide by how many in your sample. Same thing over here except plus. You got 0.53 and 0.64. All right, if we're talking proportions, we should probably speak fraction. We're saying 53 out of 100. So the true fraction or proportion of judges who are introverts is somewhere between 53 out of 100 and 64 out of 100. So if we're speaking percent, which we're not, we would say the true percent is between 53% and 64% of all judges everywhere in the world are introverts. But we're not speaking percent, we're speaking proportion, we're speaking fraction. We are 99% confident that the true proportion, the true fraction of judges all over the world who are introverts is somewhere between 53% and 64%. All right, guys, that's all I got for you.